Hey guys, welcome to this free lesson on extreme values of functions on closed intervals. The way that these videos work, you want to pause and try the examples when you are prompted, and there are free guided notes available at divideandconquermath.com that you can access. As a note, if you want to support free math on the internet, please consider liking my videos, subscribing and sharing my channel, or leaving me a comment. Okay, so let's get started. So I just want to explain the idea behind this before I go into all the theory. So I've drawn two graphs here, and you'll see that I've labeled these A's and B's. So this lesson, it says that it's about closed intervals. So a closed interval would basically mean that you have some defined area that you're going to have your function exist in. So I want to just show you two different totally random functions I'm just making up right now. So here's one, and then here's another one. Okay, so these are functions that exist in a closed interval from a to b. They don't go past that point, and they're closed, which means that these endpoints here, these exist. So very important that you just kind of understand what it is that we're talking about here. So I have a really basic question. In just looking at this graph here, can you see a definite highest and lowest point, a maximum and minimum? And yes, you can, right? So the minimum is right here, and then the maximum, so like I said, I kind of drew these at random, so maybe like both of these look like maybe they're about the same. These are both kind of our maximum. Okay, so let's take a look at this in the other graph. So just taking a look at this, where would the highest and lowest point be? Well, in this one, you can tell that there's the maximum right there. And then where's the minimum? The minimum occurs somewhere around here. So the idea behind this is that with any closed interval that I draw for you, you can always do this. You can always say there's a maximum and minimum just by picking it out. And you can actually see kind of the nature of how this works. It could occur somewhere on these curves, or it could also occur at the endpoint. But this is something that is guaranteed to always exist, and so what we're going to explore in this video is kind of all of the theory that supports this very basic idea. So first things first, I want to just make sure that we all know what the terms maximum value and minimum value mean from a mathematical standpoint. So if you need to, just pause this video and write down these definitions. F of x has a maximum value at a point C if f of x is less than f of c for all c in the domain. So any other value outside of this c will be smaller. And then f of x has a minimum value at a point c if f of x is greater than or equal to f of c for all c in the domain. So c is the smallest, anything else would be bigger than it. F of anything else would be bigger than f of c. So that's what it means to be a maximum and minimum. Like I said, I would write those down if I were you, just so that you have them kind of for notes or whatever. Now, there are some other words for absolute maximum and minimums. We also use the word extreme values and global maxima and minima to talk about those terms. So I would write those down as well. And now we can go on to talking about really what that idea was getting at. So we have the extreme value theorem. Pause the video and write this down. Hit play when you're ready. So the extreme value theorem says if f is continuous on a closed interval from a to b, then f has both a maximum and a minimum value in a to b. This is literally trying to get at what I was showing you in these first two examples. This idea that I just drew two totally random functions and picked out the maximum and minimum. This theorem says this will always happen and that we can always do this. So this is a very important theorem. Also, we're going to take a look at some examples that are associated with this. So I would make sure that you have this written down just so that you can reference it a little bit later on in the video. Now, I want to show you a few ways that extreme values can actually happen. So I have here just a couple of graphs, and we're just going to pick out the extreme values or the maximum and minimum in each. So in this case, I have a maximum here and a minimum here. So this is a case where the maximum and minimum occur on the interior points. So let's write that down. Now for this other one, look at where the maximum and minimum occur in this case. I've got this and this, so this point here, this is my maximum, and this is my minimum. So from the standpoint of the closed interval, these are actually the endpoints of the interval, so let's just go ahead and label that. Okay, so let's take a look at two other situations. So once again, just note where these actually occur. With this next graph, here's my minimum, here's my maximum. So here's a case now where one occurs at the endpoint and the other occurs at an interior point. And this other example is showing kind of the same, just kind of inverse relationship, right? So here's my maximum and here's my minimum. So you could have any combination. You can have your maximum minimum occur on the interior, or they can occur on the endpoints, or they can occur in a combination of the two. So let's write that down. Okay, so that's all the ways that extreme values can occur. Now, I want to take a moment here to take a look at a few exercises that really explain the extreme value theorem. So what I want to do is I want you to sketch the graph and determine whether the function has any absolute extreme values, and does this contradict the extreme value theorem. So let's start with this first function. So what I want you to do with the examples that I'm going to show you is I want you to actually draw out the function. So I'll use the white color here, and let me draw this out. Okay, so here's what my function actually looks like. And remember, we're doing this on this closed interval, so this is going from -2 to +2. That is the closed interval that is defined right here. So first things first, do we see a maximum and a minimum value? Yes, we do, right? We can pick them right out. So here's my maximum, and here's my minimum. And if we go back to just looking at what the extreme value theorem says, so this falls in line with it, right? We have a continuous function. This is the thing that you need. It has to be a continuous function on the closed interval. So if I look at my example, it is indeed continuous, so we have that maximum and that minimum. Okay, so now what I want you to do is I want you to pause the video. I want you to take the time to draw both of these, and then I want you to determine whether or not there's any extreme values. So same thing as the last exercise. Hit play when you're ready. So I went ahead and I drew out what this first example looks like. So I have 1 over x squared. So it's going to have kind of this behavior where it's going up from -1 to 0. So it will never actually touch 0. And then for x plus 3, so then we've got this line part going from 0 to 2. So this is indeed on a closed interval, right? So this is all closed. But there's a big problem. There is not there is a minimum value, right? The minimum occurs here, but we cannot see a maximum value. You might think, oh, isn't this the maximum value? But it's not, right? Because this function here is just going to continue to go up for forever. So there's no minimum value. So now we have to think, does it actually contradict the extreme value theorem? But it does not, right? So if I go back to that theorem, it says that once again, f has to be continuous on a closed interval. And if you look at the graph that we have, it is not continuous, right? There's this gap right here. So what we can say then is there is no maximum. There's no maximum because the graph is not continuous. So if you don't meet the criteria that are kind of stated in the extreme value theorem, then all bets are off, anything can happen. So what about the other example? Okay, so there was a little bit of a twist with this one. I wanted you to note here that this is not less than or equal to, right? This is just less than. So to graph this out, that means that I have these open dots. So this is, again, kind of a strange case. I can see the maximum here, but I don't actually attain the minimum. And the thing about this is if you have an open dot, then you really can't get to the bottom of the minimum, right? Because the smallest point I think that I might get to 0, I can always find one that's smaller. So this open dot creates an issue, so the interval is not closed. So no minimum because we don't have a closed interval, so extreme value theorem won't work here. All right, so let's keep going. So I have drawn here another graph that is on my closed interval from A to B. And my question is, what do you notice about the tangent lines at the peaks and the valleys? So if I take look, here's a peak, right? What can I say about the tangent line here? It would look like this. What about here? Here's a valley, and my tangent line would look like this. And what about here? Well, here my tangent line would look like this. So this is kind of an interesting thing to note, because you get several pieces of information about this. First of all, is this a maximum? No, it's not, but what if, so just playing around here, what if I cut my interval off from here to here? Would that then be a maximum? Yes, it would be. So it's almost like this is like a pseudo maximum in some cases. You could think of it like that, and we actually have a term for this. So this kind of acts like a maximum. This is definitely a maximum. When this happens, this is what's known as a local maximum. So that's one thing I'm going to show you the definition of in 1 second. But the other thing I want to notice with this, what is the slope of these tangent lines that I drew? Well, these are all horizontal, so these all have a slope of 0. We're going to dissect all of that with the next definitions and theorems. So first, going back to this idea right here, so this would be what's known as a local maximum. And what is that? So here's the definition. A function f of x has a local maximum at a point c within its domain if f of x is less than f of c for all x lying in some open interval containing c. So this idea of some open interval, that is kind of open language in some ways. So it's that idea that I just took and kind of randomly drew this and said, well, if this were my interval, right, then this would technically be a maximum. That is the part of the definition that's kind of allowing me to do that. So I would highly recommend that you write this down just so that you remember it. And then we also have, of course, a local minimum, almost the same definition, right, with just a few tweaks. I would highly recommend that you have this written down as well. These are two very important concepts. And just as a note, another word for local maximum or minimum, minimum or maximum, whichever, is relative extrema. Okay, so now what I want to do is I want to think about those peaks and valleys. Those peaks and valleys actually create or represent what we call critical points. So an interior point of the domain of a function f of x is a critical point when either you have the derivative equal to 0 or the derivative is undefined. So this we can really clearly see if we think about what this means. So the derivative stands for several things, right? It stands for, of course, the derivative, but it also stands for the slope at a point. So this is saying if you find places where, the derivative equals 0, that means that the slope at that point equals 0, which is exactly what this situation here is, right? The slope at this point would be equal to 0, and so this would be a critical point. So there's this kind of interesting relationship between the derivative and what's actually happening on the graph. So this can also happen when f prime of x is undefined, and we'll see some examples of that as we go along here. So now I want to go back to this concept of closed intervals. So I have my two closed intervals here, and I want to think about then what could I actually do to figure out what the extreme values are besides just looking at the graph. I know that looking at the graph is like definitely the simplest way to do this, but we need a more mathematically rigorous way to get to this. So in this case, think about where the maximum and minimum are. First, let's just note those. So now that I see these points, so what can I say about them? These are critical points. So in this case, the maximum or minimum occurred at the critical point, and I would find that by setting the derivative equal to 0 and figuring out how to solve that, or figuring out where the derivative does not exist. So this tells me a lot about how to find extreme values, but only in some cases. Here's my other case. Now, in this case, my extreme values do not actually occur on the interior, right? Where do they occur? Let's mark them. In this case, my extreme values occur on the endpoints. So in this case, if I just plugged in the endpoints, I would, in theory, then see that those are the maximum and minimum. Well, it turns out that these are really, this is the exhaustive list of how you find extreme values on closed intervals. You either have the critical points, so let's maybe write this out. So how to find absolute extrema on a continuous function f on a closed interval. So first you can find all the critical points of f on the interval, so start with that. And then the other part of this would be this situation here. So this would let me continue my list. So I'd have to find all the critical points, but I'd also have to evaluate the endpoints. So I find my critical points, and then basically what you're going to do is plug in your critical points into f, not f prime, you're plugging it into the regular function f, and then you're also plugging the endpoints into f. After you've done that, all you have to do is take the largest and smallest values of these. So this is actually a really nice, straightforward process when we have a closed interval. So now I want to find the critical points for the function and then determine the absolute maximum minimum on the given interval. Okay, so let's go ahead and do that with this example. And what I'm going to do is I'm actually going to outline these 3 steps, and I'm going to number them just so that you know which step I'm on from the notes. So first things first, I'm supposed to find the critical points. So I have to find my f prime of x, which in this case is going to equal 2x to the 4th. And then for my critical points, it's either where this function is undefined, and if you think about this, this function has no points where it's undefined, right? So we'll see some examples where that happens, but this one does not. So I just have to think about where will this equal 0, and this will equal 0 when x equals 0. Okay, so that's step 1 of this. So in step 2 now, what I have to do is I have to evaluate f of each one of the critical points. So I need to plug in not f of the critical points, f of the critical points and endpoints. So I need to plug in these 2 endpoints and also this all into my f of x. So I'm just going to go in order here. So starting with f of -1, so if I just plug this in like so, this will give me -12 over 5, or that equals -2.4. So now moving on, I'll move on to f of 0. So if I just plug f of 0 into this function, so this will just equal -2. And then finally, if I plug in f of 5, so I have 2 to the 5th times 5 to the 5th minus 2. And this comes out to 1,248. Okay, so in looking at this, so this is actually all you have to do when you have a closed interval to figure out the extreme values. So looking at this, which one is the smallest value? This one here. This is my minimum. And then for my other one, this is my largest one, right? So this is my maximum. And so this is really what you have to do. So then for step 3, you would write out that those are your minimum and your maximum. So it's just taking those largest and smallest values. So maybe we'll just label this as the step 3 here. Okay, so that's really the idea behind this. And the whole thing with this is only going to work when you have a closed interval. So you want to keep this in mind, okay? So now what I want you to do is I have 4 examples here for you to try of this idea. And you're going to have to stay on your toes while you're working with this to make sure that everything's working out. Hit play when you're ready. Okay, so following the steps from before, the first derivative of this is going to be -x to the -2nd. So this one's going to work a little bit differently now, right? If I wanted to write this out, this would be really -1 over x squared. So where does this equal 0? It does not. This will never equal 0, right? However, this totally has a place where it's undefined. So where is this undefined? It's undefined at x equals 0, because you can't have a 0 in the denominator. So in this case, this would be my critical point. So now I've got my critical point here, and then I have to test my endpoints. So now let's plug those in, going in order. Well, you need to start really with the endpoint here, and so you'll notice there's a big issue actually with this. Is 0 in this interval? It's not, right? So even though I found this point, this actually won't work in this case. And now if you think about this for another moment, this should make a little bit of sense. Well, and maybe sense is the wrong word, but there's actually an issue with this function just if we didn't have a closed interval around it. At 0, there is actually an asymptote, right? So this function is not actually continuous, but it is continuous just on this little closed piece if you were to graph that out. If I included 0, I would have a big problem with this because then I couldn't use the extreme value theorem, but as it is, it's hunky-dory. So I found a critical point in this case. I can't actually use it, so that means I just test the endpoints. No problem. So let's do it. Okay, so this one actually becomes super simple. This will be my maximum, and this will be my minimum. And so that's all you have to do for this one, because you don't even have your critical point in your closed interval. And that's okay. That's going to happen with some of these problems. Okay, so let's move on to this next one. First things first, I need to find the derivative. And now I need to think about either where this function equals 0 or where it's undefined. Now, we know that we need to figure out where this is 0 or undefined, and maybe you're having some troubles with that, so you can always rewrite this in this form, right? So secant is 1 over cosine, and then tangent is sine of x over cosine of x. And you could think about this function here, right? This is the same thing. So where does this equal 0 and where is this undefined? And if you think about it in this terms, so for all fractions, they always equal 0 where the top equals 0. So if I just think about where does sine of x equal 0, where would that actually be true? So that would be where x equals 0 or pi or etc. If I kept going, maybe around the unit circle, 2 pi. But this totally doesn't matter in some ways, right? Because you have to really, as we just saw in the last example, you've really got to pay attention to what's going on in the closed interval. So the only value here that actually matters is just x equals 0. So that's where the top equals 0. And then you have to think about for where is this undefined. So with a fraction, or with a rational expression, this will be undefined when the denominator is 0. So I really just have to think about where does cosine of x equal 0. If I know where this equals 0, that will make the whole thing undefined. And so you might want to bust out your unit circle here, but this would happen at like pi over 2, or 3 pi over 2, or depending on how you're looking at it, negative pi over 2. But which of these values actually matter? Well, in the context of our closed interval, actually none of them matter. We don't have to worry about any of them. And maybe I kind of overdrew there. So none of these can happen in this closed interval. So there's actually no place where we have to worry about this being undefined. So if you're playing along at home here and you're paying attention, this is the critical point in question in this context. It totally is dependent on your closed interval, okay? So now I have to plug this in for my critical point and my two endpoints. So let's do this. So remember, you want to plug each value back into the original function. So if I keep going, here are the three values that I get. So now we have to select our maximum and minimums. So in this list, this is going to be the maximum, and then this one here, this is going to be the minimum. And so then you'll just want to pay attention to the format of how you need to state that. So as a point or as the actual maximum or minimum, so just pay attention to that. Okay, so moving on, I've got another one here where I have to take the derivative and find the extreme values. So let me start by taking the derivative. And so for this one will not have any undefined values. So if I go and just set it equal to 0, so I'll just get that x would have to equal 0. So there's my critical point. So once again, I'm now going to plug in this and the endpoints all into our original function f of x. So let me do that. And so from here, once again, I can figure out my minimum, which is going to be 0, and my maximum, And so those are going to be the two points. And now for this last one, so once again, let me find the first derivative. And so now for this one, for my critical points, so this will not equal 0 once again. So if I were to try to set this equal to 0, so this would really be 2 over the cube root of x. Where does this equal 0? Well, 2, the top part will never equal 0, so this whole thing will never equal 0. So you just have to worry about where it's undefined. And so it's undefined at x equals 0. But once again, that doesn't really matter, right? Because that's not part of our closed interval. So that means that my maximum and minimum are really going to just occur at the endpoints. So I just have to plug those in. And so in this case, this will be the minimum of my function, and this will be the maximum. And so that's the whole idea with closed intervals. So this is a really nice straightforward process with closed intervals. Of course, you know that we're going to take a look at cases where we don't have closed intervals, and then it won't be quite so straightforward, but that's kind of the idea. So thanks for watching, guys. I have a lot more videos on all sorts of calculus topics, so I hope to see you in another one. See you next time.